Yo, what is up everyone? This video will be doing the projectile system as in the title. So this system's going to be for things like any bow and arrows, any guns, anything that's like throwables even, and it's just anything projectile based. So this will be based on a fast iteration. So we'll do very small amounts of data, we'll do very quick updates, we want to do step by step rather than bulk steps for one projectile at a time. It'll be too slow. And this will follow the style of a behavior tree system I've implemented, which I may do as another video. So to get started, we're just gonna have a basic idea of what we want. So when we think of projectiles, let's do bullets as that's the easiest. So when we think of a bullet, we've got this little block that travels in a direction. So that's its velocity, that's what we call it, the velocity of a projectile in motion, basic physics. So that'll be pointing in some direction, in this case it will be this blue arrow, and we can do like straight ahead. And then also we have additional forces being applied to this, which is gravity, we can have acceleration, so air resistance, we can apply that if we want. And we need to support these in our projectile. So we know for a fact that we'll need to... Oh, actually the front's this way. So we need to make the projectile traverse in the direction it's facing. It would be at a specific speed. We need to add a acceleration to it. So every time we update the projectile, we'll apply an acceleration, gravity, air resistance, whatever. And then we need hit detection. So we have a couple ways of to do hit detection. We can do projectile raycast. So we'll just raycast straight in a front line a certain distance. We've also got shapecast. That'll be more for mesh parts that you need to shapecast the entire mesh forward. And then we can also do some basic box detection, get parts in part, things like that. But for now, we'll just do some basic raycasting and you can edit the system as you need. So I'm going to split this up into two parts. We're going to have a normal script and we're going to have a module script. So we'll have this as a separated abstracted system. What I mean by that is we'll create projectiles in this code here, and then we'll handle all the hit detection, all the damage, all the whatever we want in the actual script where we create the projectile. So I'm going to do a struct-based instead of a class-based, as having a struct-based system will be much faster than having a meta table, as you have to go through the meta table first before you get to the data, and that's just gonna have way too much overhead, especially when we have tons of projectiles. So what I'm thinking is we'll come up with a basic outline. We'll have our projectile module, script.parent, wait for child, projectile. And then what we'll probably do is have a bullets, or actually in this case we'll just have projectile module.create projectile. We'll also do a start and a init. We'll just have these in case you guys want to add stuff into this, init and start functions. But we'll create a projectile, and then we'll add projectile to system, or we'll just do add projectile like that. So if you have custom projectile data tables, you can just put that in there. And then, yeah, actually I'll put this in lowercase just so I know. And then we'll do like, on hit connect function. So we'll have events like that. Actually, I'll do bindable events for now, but if you're doing custom events, you'll do that, or script-based events, pure Lua events, whatever you want to call them. And then we'll have our hit there, or a recast results, like that. Now in my other projectile system, I actually had it so you would have a function which tells you whether or not the projectile is continuing and what the state of the projectile is after the update. So what I mean by this is if I have a onRayHit equals function, we'll have our projectile, we'll have our ray result, raycast result, question mark, which I'll do like that. So onRayHit, onRayUpdate. Actually, this should be a on projectile update. on projectile hit, on projectile terminated. In this case, we could probably just not have projectile as the first argument because it is inside this projectile object. But we can also do on projectile updates, equals function projectile. We could do something like that. I probably will just leave it as this. So we've got on hit. Oh, that's meant to be on terminated. So just kind of thinking about what I want in the projectile. I want it so when the projectile moves, we can update it. I want it so when we hit something, the projectile can update itself and tell you whether or not it's ended, if it's terminated. And then when the projectile terminates, we can clean up any like visuals we've got in this server script here. And then we've also got event-based stuff, but we could probably move that externally. On projectile hit. So this could probably be projectile hit event, connect function, projectile terminated event, and projectile update event. Something like that. That's probably better. And then we'll add it to the system, or we'll do register projectile. Here I'm going to pass in a property table like that. I think that should be good for the start. And then projectile Z, I'll put delta time there. Do you want? I'll probably put projectile in there. Because if I do this instead, like that, we can actually save these functions and use it for any projectile. So if I come back up here, I'll do default projectile update, like that. And then any projectile we create, we can just have this be used for that. And I find that to be a much better idea. So I shall sort these out. Default projectile update, default projectile hit. So this one's actually going to return a number, which we'll discuss in a moment. So that will be what we want to do with the projectile when it hits something. We're going to do default projectile terminated. This one I don't think we'll actually need. There's no reason to have a callback like this. It'll just be better to have an event. So we'll just remove that. And then what could we do in the updates? I don't think this update one will be efficient as well. This one specifically here. Because we'll be running this every time we update the projectile. Callback function slow. And there's not many use cases for this. Because you can just remove the projectile from the... It's like how we register it, we can remove projectile as well. So like if we terminate the projectile, we can remove projectile. Or we can terminate projectile as well. Like that. So that's something we can change there. Look at our properties here, so we can do like lifetime as well. Yeah, I'll get rid of that. For now, I'll just return one here. Alright. So I think that's what we're going to start with. We'll start with this. So let's come over to our module here. So this is starting with the use case, what we want it to look like when we're trying to use it. Sometimes you might want to start in here, just basic stuff, writing down what you might need, and then figuring it out from there. But because we're doing this in a practical sense, we do want to see what we may need when we're doing projectiles. And this looks pretty good for the start, so we'll start with this. So let's come into here, let's create these functions. down here. So we'll have create projectile. In this case, I'm going to have a properties table. We'll talk about that in a minute. We're going to have a register projectile. So that's projectile there. Oh, we'll do create default projectile. We'll do remove projectile. We'll do terminate projectile. And then, is that everything there? Yep, these are projectile specific, we'll come back to, and we've got init and start as well. Function module init, function module starts. So that's all good there, and that's our basic system there. So let's move on to doing the actual implementation of this. So we need to think about how are we going to calculate how this projectile is moving around. So how will we know how this projectile is moving around? What we need to know is the projectile motion formulas. So these will tell you where the projectile moves during time, based on its like velocity, acceleration, and we just want to get some formulas that will tell us how this projectile should move. Now the ones I'm specifically talking about are these equations of motion in a straight line. So looking at this here, we've got our final velocity is our initial velocity plus acceleration times time. We've got our displacement. So this is where our projectile will, or how our projectile will move, given the velocity, time, acceleration. And then we can also figure out the final velocity given the initial velocity plus the acceleration and displacement. So this will give us the final velocity, the position that it's now at, after a certain amount of time has passed, and we can also figure out the final velocity from the non-displacement, non-position changing stuff. So we can just figure out the velocity without actually having to move the projectile at all. And then we've got some other things here we can look at. We've got projectile motion here. We've got like plane, time of flight, maximum height, the range, so how far we'll go forward. We can use all of these formulas here to do that, but we don't actually need to do that. That's only if you want to visualize the projectile path and that sort of stuff, but we don't need to do that. We can just focus on these motions in a straight line. So we're going to implement those. I would recommend you have a look here and start typing these out. So I'm going to move this over here. I'm going to open up this here, and we're going to do local function. And looking at this formula here, we've got final velocity u plus at. So I'm going to call this find final velocity given, what would it be? Given acceleration. Find final velocity given acceleration. Find final velocity given... Oh, we can actually just say Formula 1, Formula 2, Formula 3. So that is... I'll move this over here so I can do it. So V equals U plus AT. We've got S equals UT plus 0.5 AT. Where are my T's? There. 2. So just heads up, this double times here means to the power of, because in other languages, the up arrow actually means a binary operation. And we don't want to do that, so we want to do to the power of instead. And then we'll have also V squared is U squared plus 2AS. So we've got final velocity given acceleration. We've got displacement given motion. Given motion in time, or in period. And we've got final velocity given displacement. or given motion. There we go, that might be better. What I've got is our final velocity. So in this case, we're doing vector 3, three-dimensional projectiles, is our u, our acceleration, and our time is a number. And then we'll just do u plus acceleration times time. So remember, this is a vector 3 times a value or a number. So that will scale this vector 3 up, and then we'll just add the two vector 3s together. And that will give us our final velocity. For our displacement given motion in period, we've got our u, our t, our a. So our initial velocity, our time period that we're talking about. And we've got our acceleration. This will give us a vector 3 offset. We're going to return our u times t plus 0.5 times a times t to the power of 2. In this language, t to the power of 2 is 2 squared. Oh, t squared, or to the power of 2. Another important thing is that we've got to put brackets. We're going to put parentheses around these so it does the operation correctly. What we can always actually do is local equation 0 is u times t. Local equation 1. So we're starting on this left side of the plus, and we're doing the right side of the plus, or the addition, and we'll just add them up in the end. Like that. That might be better for you. And then down here we've got our final velocity. Oh, sorry, we're finding out the final velocity. We're passing in the initial velocity, we're passing in the acceleration, and we're passing in the displacement. And these are vector 3s. We're going to return our u to the power of 2. So actually, let's do the same thing. Equation 0, that is u to u squared, and then we've got equation 1 is 2 times a times s. So we've got that one plus that one, following that formula there. And remember, we're returning the squared final, so return final velocity square. We'll mention that in the function name so we know. Squared. As if we want the actual velocity, not the squared velocity, we'll have to square root it to cancel out the power of 2. Alright. So now that we've got our physics formulas, we can now apply them. So what we're going to do is just think about this for a moment. So every time we update the projectiles, we want to figure out the displacement. So that is now where will we be after a certain amount of time has passed. And we want our final velocity. What is our new velocity after this amount of time has passed? And we want to use them as that will be important. So we need our current position, and we might want our previous position, and we might want to calculate our next position. So that way, if we have a look in Paint, so this is our projectile, with our previous position, and we'll get our next position. So that will be, it's now going that way, but previously it was going up that way. And then we can do like a curve there. Alright. So let's go into our projectile here, and we need to figure out what we want our projectile data to be. So we know for a fact we're our U0, I'll do in normal names, initial position, we'll do our, for simplification, let's do our origin and velocity, or position and velocity. So let's do vector 3 to 0, velocity. So this is current location, this is initial location, so this is origin position, this will be origin velocity, or I'll call it initial, that might be better. Initial location when projectile was made. That'll be important later, especially when we're doing visualization. And then we want time elapsed. We want to know how much time has elapsed. We want to know the lifetime of the projectile. So if we want it to be, if we don't want this projectile to last infinite amount of time to it crashes somewhere, we can put a lifetime on it and it will automatically remove itself when that time has passed. We've got our callbacks. So we've got our on projectile hit. We're going to actually move this inside this code here. And I'm going to have it at the top here. Default projectile hit. So this will be on projectile hit equals default projectile hit. Let's remove that. We want our events. So this will be instance.new bindable events. Fix. I'll just put this here for now, but we're going to use this .event here. So usually if you have your own custom event module, you'll just do like event.new, and then you just do connect function, whatever onto that. But for now, we'll just do that. So we know it's talking about specifically the event part. So we got our hit event, we got our terminated event. And then that's it so far. We got our basic data there. Let's see what we want to think about next. So we've got our current position. We need the last position as well. So the last position can be very helpful if you're doing visuals as well. So we might want to add that. So last location, last position, last velocity. And then that should be good. And then we can get to delta as well from the last to the current if we ever need that. And apart from that, what else can be used? Oh, raycast. When you think about the raycasting here and shapecasting, so you can have raycast params. So we might want to include them. So we'll do raycast params. For now we'll just do nil. We don't have any. We don't need overlap params. So what else do we do in raycast? We've got the position, we've got the direction, we've got the raycast params. I can't think of anything else right now for that, so maybe we'll just start doing some of the code. So we'll be doing this every update possible. So we'll need a run service loop. We'll be hooking into either render step or heartbeat, depending on if we're server client. So let's just do a if run service is server, and this is heartbeat update, else render steps update. And actually, let's flip this is client in case anything breaks there. So if we're on the client, we can use the render steps. If we're on the server, we cannot. So let's just connect that. Let's do DT for delta time, which I might do that. So how much time has passed since the last update? Same with heartbeat. Now the difference between these is render steps runs, I think it's every frame, no matter what your frame is. Fires every frame prior to the frame being rendered, and then heartbeat is at a certain rate, it will do it. Oh no, fires every frame after the physics simulation has completed. And was this before it? Prior to the frame being rendered. Oh yeah, I'm not sure about that. Or was it, maybe we could do like pre-simulation. That'd be better. In that case, we don't actually need to do that anymore. That's the old way of doing it. Usually it meant heartbeat was at 1/30. So 30 times a second. Render step was 1/60, 60 times a second. That was the difference. But with this, it'll just follow the frame rate, which is great. So we want to do it before any objects update, and then we don't have to deal with any crap. And then what we can do is come over here and start coding the internal stuff. So every time we update, we want to update all the projectiles. So we'll do internal update projectiles delta time. Oh, and also I might do a separate function here called auto update projectiles. So let's do a function for this. So this will enable auto updating projectiles, manually step projectiles. So this way we can run this code here. And then that way if you want to do custom updating steps, you can do that easily there. And then what we'll do in here is if not module.auto updating enabled, then we'll just do that. So this is to stop you from spamming this. And then we can just do that in there. And then we can just simplify this down to that. And we'll also, just to make sure we have it here when we're doing code completion, we do that there. Like that. Okay. And then you can yourself edit this if you want to have it so you can turn it on or off by disconnecting that event there. But for now, I'll just simplify it to this. So we're going to auto update projectiles, we're going to register a new projectile, and then we'll just let it do whatever, and we'll have our events and stuff here. So let's start with this internal update projectiles. So we're going to iterate over all the projectiles, so we need a table for all the projectiles. Module active projectiles equals a blank table. And then we'll do for underscore projectile in module.active projectiles do. Now there's a slight problem here. When we want to remove a projectile from this active projectiles table, we can't do it here because it will mutate this and we'll end up skipping projectiles as we go up the iterator, or may even restart the iterator from the left. So what we want to do is actually take a different approach to this for loop, where we have a local index equals 1, while index is smaller or equal to number of module.active projectiles do. And then this way we can say local projectile equals module active projectiles is index if projectile.destroyed else index plus equals 1, and then we'll do updates here. So this way we don't restart the iterator when we remove a projectile. We stay at the current index, but we remove the value that's at right here at this spot. Like so. So let's say a projectile was destroyed. We're going to remove it from the current spot, and then that will move everything from the right of it to the left. So we'll take the spot, and then we just continue on. We do this loop again at the same spot, and we update the next projectile that was moved here. And then we can just increment if it's not destroyed. Now, of course, since we've added this here, let's do destroyed equals false. Actually, I might do terminated. Let's do terminated instead. And then we're going to do our update code here in a moment. Now, there's actually another thing we can do to optimize this further. Pre-optimization is killer, but this one is easy to optimize. We can actually count from the end of the projectile list from right to left. No. Okay, so now that we've done that, let's do our next part, updating. So since we want this to be like sort of async really quick, we don't want to hold this up, this main loop here, from updating all the projectiles at once. So we want this iterator to be as fast as possible, but we still want the projectiles to update even if they're not synchronous together. They can be async from each other, as these projectiles can't collide with each other at all. So there's a little trick we can do here where we have a is updating equals false, and then we use this flag to tell us whether or not we can actually update this. So if we say projectile, so if we are updating, sorry, other way around. If we are not updating, we will begin updating, and then we can do a pass.defer. Let's do a defer. So defer is, oh, will it give us it? So it will call resume a function coroutine at the end of the current resumption cycle. So what it will do is it will finish running all of the code in the current cycle of the scripts. So it will run all the other modules codes or your other game's code. And then on the next script cycle, it will start running this code. So this is great if you have a lot of other things going on and you don't want this to run immediately. And yeah, I find this just to be a lot better because if you do spawn, that means do it now. But we want to defer it and let everything else finish first. Especially this. This means it will let all of these finish first and then it will start running these. Right here, so if we are not updating, we'll force it to be updating to true. We'll run the update here. And then we'll set this back to false. So that way, it will allow it to update again. But we are putting it in a separate thread, so it doesn't yield this entire loop up and lets all the other projectiles update at the same time. So now that we've got that, we can actually run a... let's actually remove this internal part here. This should be the internal part. Update projectile. And we'll have our projectile. And we'll have our delta time. So let's take this. We'll be calling that here. Like so. So we're going to pass in the projectile. We'll pass in the delta time that has passed. Like that. And another great thing about this is even if the projectile doesn't update in this cycle, it will start updating again in the next cycle. Especially when this is called multiple times in really quick succession, it doesn't allow it to update either because it's already busy updating. So you won't have any problems where it will collide during the update. And it would like double step and trigger the same hit. So now that we've done that projectile update loop, we can move on to this internal update, which is on a per projectile basis, what do we do? So let's think about what we do. So we have our projectile. We want to figure out the next spot it's going to be. So where this F is, for example, we need to raycast in between these two spots so we can see if we hit anything. If we hit anything, we've got to go to this function here. This will tell us what to do. So let's say 1 is stop, 2 equals continue. So we'll start with this. Then when we return 1, we'll stop the projectile, we'll terminate it. Actually, I'll call that terminate. And when we hit 2, we'll continue going. So we'll ignore that recast result. And we'll just keep moving. And then, depending on what that does, we'll terminate or not. And if we don't terminate the projectile, we'll keep moving on. Or we can ricochet or reflect, for example. Whatever you may desire. So what we're going to do now is take this projectile here. We're going to call this... no, we're going to get these position and velocity values. And we're going to figure out the next position and next velocity that we'll be at. So we'll have to use this formula here. The displacement is the current velocity times time plus acceleration times squared. And half that. So we're going to do displacement is the projectile.velocity, the elapsed time, which is delta time in this case, and the projectile's acceleration. And there's another thing we forgot. We've got the projectile's acceleration. So let's do vector3.0. Last acceleration, vector3.0. Initial acceleration is vector3.0. So we'll add those in so we know. So that's our displacement. So from our current position, where are we next? So this will be next position is projectile dot position plus displacement. So that's now where we are next, and then our next velocity is a vector3, which is what is our velocity given the acceleration. So we can actually pick this option here because it will be much quicker than doing these operations down here. So we'll do that. So we want our current velocity, we want our acceleration, and we want the delta time. So same values here, but in a different order. There we go. And we can simplify this a little bit. We can just swap them out. We our next position, next velocity. Now, let's actually have a look at this. So let's grab this code here. And let's do a little bit of manual work here. So I'm just going to comment all of these out. Let's do our module. We'll just pass in a custom one, and we'll do 1 second of motion. We'll get our position, vector3.0. Our velocity is vector3.z-axis. We're moving along the z-axis, and our acceleration is vector3.0. So just by looking at this, after 1 second of motion, we should be 1 stud on the z-axis positive. And then if we come over here, let's create an attachment. Start attach equals instance.new attachment. Start attachment.name equals origin. .visible equals true. .parent equals workspace.terrain. And then our final attachment. This is our next. So we'll do final attachment .world C-frame is our next position. And the start attachment world C-frame equals C-frame.new, the current position. So this will show us our before and after movement. So we play the game here. And I should probably anchor that. So we should have some projectiles here. So there's our before displacement and our after. And because it's displacement, it's not local, we actually have to do a... Oh no, sorry, that is correct. We're in the middle here. So our initial position is 0, 0, 0 in the middle of the world. Our velocity then, after 1 second, moves us 1 stud on the z-axis positive. So this is correct here. This is what it should look like. And actually, what we can do is apply some gravity if we want. So let's do vector3.y-axis, and we'll put a minus sign here, so it's pointing downwards. So we should get like a... There we go. So that is 1 in the positive direction, and then 1 down for gravity. And then if we try that again, but let's apply our position, next position, velocity, next velocity, and then we'll just leave the acceleration as is. So we've done that once, and then let's just run it again. So we'll just take this out here. Let's do a couple times so we can see what our movement looks like. There we go. So that's our projectile now moving. And because we have called it 1, 2, 3, 4 times, so 4 seconds worth of motion is this. So as you can see, we've already got our projectile motion working. This is now partly working, a partly working projectile system. Now we just need to automate this, add the events, all of that jazz. The next, let's just clean this up. And then we need to do a couple of things. What we need to do now is have a look at our code out here. And let's actually change this back to what it was before. Just these ones. Our position, let's do like vector3.new 0, 10, 0. So up in the air. Our velocity will be vector3.z-axis times 5. So we're going 5 slots a second, positive z-axis. And our acceleration will be gravity in this case. We'll just do vector3.y-axis minus there, and we'll do 9.8. In this case, actually, we can just do times minus 9.8. And then when we update, we'll move the projectile. When we hit something, we'll figure that out. And when we terminate, we'll do some stuff there. So let's take, I could probably use an example here, actually, what we will use these events for. So let's say we have a beam that represents a projectile. We can move this beam by using these events. So when the projectile updates, we'll get the current position, the previous position, and we'll make a beam between them two. So what we can do here is attachment 0, instance.new attachment. Attachment.name equals the start. Attachment 0.parent workspace.terrain. And let's do the world C-frame. No, we want visible. We're going to make it visible. And let's do attachment 1. And let's do a beam between them. The width 0, 0.1, beam.width 1, 0.1, beam.parent is, we'll put an attachment 0. Transparency is a number sequence.new, we'll do it half. Base camera is true. So we just have a look at this right now. We should just have, oh, it's not, they're in the same block, so you can't even see it. Attachment 1 dot position is vector3 dot z-axis, like so. So that's our projectile there. And then we can move these two attachments to show us where that projectile is. So if we have a look here in the update events, let's do attachment 0 dot position is projectile dot position. Actually, we'll do world C-frame here. Let's just make sure we do that, even though I do position up here, but whatever. Attachment 1 dot world C-frame, C-frame dot new, projectile dot last position. And then hit event we don't need to worry about. And then terminate, we destroy the beam. We destroy attachment 0, and we destroy attachment 1. Oh, and actually, let's add the lifetime to this as well. Like so. And we don't want any raycast params yet. That should be good. We actually haven't set this up completely yet. We've got this properties table, but we don't actually apply it, which I totally forgot about. So let's do that. So we're going to create a function called setProperties, which is going to be object any properties is a table, and we're going to return any. So for prop name, prop value in properties, object prop name equals prop value. Now, because this table can be null as well, if type of properties is equal to table, we'll only then apply it, and we'll return the object back. And then we'll do set properties that table the properties that we pass in. There we go. And that will return a table. For now, I'll just leave them blank, but that's fine. So we look at this function. So we pass in properties optionally, and we get something back. Great. So now we've got our projectile working. We've got the events working. We've got our default hit thing here, so we'll terminate when we hit. We just need to do all the core functionality of this down in the internal update. So let's start with that. So we've got our current position, we've got our next position. We need to do the recast detection. So let's start with that. So if local result workspace, local ray result equals workspace recast, our current position. The direction is the velocity, and we've got our projectile.recast params, which is optional. And then we'll say if array results, and then we'll ask the user what to do. And we'll do that in a moment, but we also need to have a look at up here. We need to do our lifetime still. So let's do that. So let's have a look here. What is this? Projectile.time elapsed equals delta time. Now what we actually have to do as well is lock this delta time between the delta time and the lifetime, so we don't go over that lifetime value. So why do we do this? So let's say our projectile system pauses for 10 seconds for some reason, whatever reason it may be, and then it runs again. If this projectile has the lifetime of 3 seconds, we don't want it to do 10 seconds worth of delta time. We only want it to do 3 seconds worth. So this math.min will pick the lowest value between the lifetime and the delta time. So we'll just do that. And then we'll add that to the elapsed time. And if our projectile.time elapsed is larger than the projectile.lifetime, then we will destroy the projectile. We'll actually use this function up here to do it. So that's a sugar function. Let's do that, and we'll just return there. Now, some of you may want to do this recast result still before you terminate the projectile. So you can just move this down here if you want that. Which in this case I might actually do. So let's have a look. So we've got our time elapsed and our lifetime working now, so we don't need to worry about that. We just need to do the hit detection. So let's just do a little sample here. Let's just print it, and then we'll just continue on. Our hit event, we won't worry about treating these yet, because we've got to set up these events properly. Let's see if we get any results straight away. Actually, it might be too hard to see the projectile, so let's actually do these events properly. So, was it update bindable, instance.new bindable event? Was this update bindable, hit bindable, and terminated bindable. You don't need to do this if you're doing custom events. But this will be that. We can now clean that. That will be, was this hit bindable? That'll be this one. Terminate bindable. Like that. So we now can remove these. And then in our remove projectile, terminate projectile, we need to look at if projectile.terminated, then return. So we've already terminated it. And then here we'll set that terminated to true now as we clear everything. So our update bindable will be destroyed. This hit event will be destroyed. Oh, what is this? And our terminate will be destroyed. Now I can't recall if that actually kills these. Maybe I'll just try something real quick. Let's just return projectile. So if I do projectile. Oh, is that not gonna work? Oh, because of the set properties. Hold on. I just want to see if I can do it directly. Okay, so it doesn't let me do it again. So let's add these back. Properties, and we'll just return here instead. So that will have to be managed by the person, but that's fine. As actually this one can be a once. And then this can be C1, C2, C1 disconnects, C2 disconnects, and we're done there. There we go. So when we terminate, we'll destroy these bindables. We'll set terminate to true. And we'll just leave this as is. Oh, and also we'll remove projectile as well, which will be important. So for remove projectile, we'll just do local index table.find module.active projectiles, this projectile, if index then, table.remove module.active projectiles, index. Unfortunately, we can't do much about that. That's as far as it's going to be. But we can now move on to register projectiles, which will just be the same thing. If not, table.insert at projectile. And we can simplify this to if not there and add it. So register projectile will just simply add the projectile table to the active projectiles. The remove projectile will add it, or will remove it if it's found in the active projectiles. Terminate projectile will remove it and will clean it up as well, like clean up the bindable events inside it and the data, any other data that has to be destroyed. So you can edit this as you need as well. Great, now that we're done that, let's see if this will work. So we got our update event, we'll move the attachments, and for now, actually, I might reduce the speed at which this updates. So looking at this up here, I'm gonna actually bring this down here. Let's just save that. Let's do a task.spawn function while true do, local dt task.wait 0.1, update physics dt. And I should do 0.2. So we should be able to see the projectile move because we've slowed it down to 0.2 seconds. So you can see we're getting the base plate hit. What I might do is actually just do that. Was this timescale? That's what I'm thinking of. For DT task.wait. So we have timescale. This is how fast the projectile moves, and we'll just do like 0.2. So it doesn't look like it's moving much. Oh, there we go. So now you can see in the data the projectile is moving. Does not look like these are moving, however. So let's look at why that might be. Projectile update event. We don't actually call that. That's what I forgot. We need to call these events. So let's do, let's start with the terminate event. That's easy enough. Coming down here to the terminate. Let's just do a remove projectile. Let's fire that. projectile. Oh, actually, we need to do not that one. We need to do the bindable event itself. So terminated bindable. We'll fire that projectile. This does not have a recast. Our update event does not have a recast. We'll fire that and then we'll clean it up afterwards. And for the update event, we'll fire the update bindable. So this will be post update. So actually, we might want two of these actually. Let's do, oh, we won't do it here. We'll do post update event. Where is this? Post update and pre-update, just like how Roblox has it with their physics one. So we'll do pre-update bindable, post-update bindable. Let's do pre-update bindable, post-update bindable, pre-update bindable, post-update bindable, pre-update, post-update, and we'll leave it as that. And then down here we'll do pre-update, post-update. And then down here, before we update, let's run it here. So projectile.pre update bindable fire projectile. And we'll actually pass in delta time for this one. Yeah, so that's post up, so delta time. And then we'll do your post update down here. We'll pass in delta time. And now that should fire those events. So let's have a look. There we go. So it looks like our other one there doesn't update. So let's have a look why. So that is our last position that doesn't update. So projectile last position equals projectile.position. Projectile.velocity. Oh, sorry, last velocity equals our current velocity. There we go. I should probably be commenting this video. Fire the post update event. Check if the projectile is expired. Hit detection. Update the time elapsed time. Find the next position. Find the next position and velocity. Fire the pre-update event. So we'll just do that. That should be helpful for some of you. And then what we'll do is, yeah, so we're missing this last position, last velocity, as we need to tell our script where it is. And there we go. Our projectile is now moving. And then it hits the floor there. So looking at this, we've got a slight problem. This velocity is actually way bigger than what it's meant to be. So what we have to do is multiply by our delta time here. So these two do it already in the formula. We pass in delta time, but this one we have to manually do as well. And then that's it. So let's just do that. So now we should get no hit detection until this approaches the floor. There we go, one hit detection of the base plate and our projectiles going down. And then if we set our lifetime to 3, and let's print the time elapsed so we can see how long the projectile has lasted. So you can see something very, very often. We've reached 1 second. Actually, it's going to be way too slow. Let me do 1.3, so that should be about when it hits the thing. Oh, might be a little bit short. Ah, there we go. So it expired and it terminated the projectile. Perfect. That's working. And then what we can do is, if I set that back to 3, delete this print. We'll leave that timescale as is. Let's do this hit detection part. So what needs to happen when we hit detect? So we can have a... Right now it's simple. It's just 1 for terminate, 2 is for going. So let's do a local hit. Oh, where's this? State. We'll do a number equals 1. So I should probably flip it. Let's do 2. No, that should be fine. 2 is still going. 1 is stop. So here we'll do state. So if we hit something, we want to do projectile.on. Where am I? On projectile hit is the default hit. So we'll call that function projectile. What do we pass in? Projectile and the repass results. Array results. And that will give us a number. And we'll update that state with a number. If we need to terminate now. So if state is equal to 1, then we'll terminate the projectile. Yeah, we don't want to do any of these. Maybe I'll do this post update. Let me just think for a moment. Do I want to do the post update there? Or leave it to the terminate? Because when we terminate, it will set that to true. And it will destroy all of these, which is a problem for this. So maybe we should do... Let's do that. Well, the terminate will fire so you can handle any edge cases there. I'll just leave it as that because if you have a terminate event here, which should clean up anything that post update might need to clean up when that occurs. I think that's how I might structure it. That'll be the easiest thing to do. But there we go. So 2 is continue, 1 equals stop, 2 equals continue. So by default, we'll keep going unless when we hit something, we're told to stop. And then if state is 1, we'll need to stop. We'll terminate the projectile here. And then what we can also do here is projectile dot, what's our underscore bindable? Our hit bindable will fire projectile, array results, state, delta time. That's probably what we want to have. So our projectile hit, we'll get the projectile, the raycast results, the state, which is a number, and the delta time, which is a number. I don't think Terminator will need that, but this one may prove helpful to have the delta time. And that's a number. It's a table. That's a table. That's a table. There we go. And then we'll just not do that there. We'll actually just come over here. We'll print the recast results in the state in that case. So by default, what do we have up here? When we hit something, we'll terminate. So we should see this. I'm just going to double the gravity so it goes down faster. So we have 1, it should stop, yep, and it stops with a 1. And then if I come back into this module and I change this to a 0, oh sorry, if I change it to a 2, There we go. It still goes. And you can have this as any other number you want. So even if it's n equals continue. Any equals continue. Any else. Anything else, continue. Okay, we've got the basic structure down now. So now we can have a little bit of fun. Let's do... Let's think. Let's do some bulk testing with this. Let's actually make a couple additions. So I want to do this timescale. I want to make that global, I reckon. So let's do module.global timescale. One module.global acceleration vector 3.0. And then down here we'll just do times that instead. Actually, we'll just do update projectiles, delta time times the global, like so. We get rid of that now. We use a free simulation. Let's look at what was the other one? Global timescale, global acceleration. So let's look at when we update here, we need our acceleration. So local current acceleration vector 3 equals global acceleration plus the projectile acceleration. So I might just simplify that to acceleration. We also have to pass it in there. There we go. Okay. There we go. So now we've got our global acceleration and we've got a global timescale. So what I can do now is projectile module global acceleration equals gravity. So every projectile we do has that acceleration. And we can do global timescale is 0.2. So we slow down everything in the game. Our position will stay the same for everything, but our velocity, let's do a math.random. Math.random minus 0.5. We'll do that on, maybe do all axes. Oh, sorry, X and Z axes. So we're doing in a circle around this point here, essentially. And then do like math.random 1 to 10. So like we're at 10 to 80. So between 1 and 8 studs a second speed. And lifetime will be 3 seconds. Projectile hit will have terminate immediately. And that should be it. We can start with that. Oh, and let's do this as well. Equal projectile equals that. Return projectile. Projectile.initial position. Projectile.position. Initial velocity, initial acceleration, velocity, acceleration. There we go. And we can move these to the bottom. Like that. Perfect. So that should just work normally again. Wrong number of arguments. Let's have a look. Oh. No, that's correct. Oh, vector 3. Got you. So we should have, yep, projectile went way over there. Terminates on hit. And it would be a good idea to remove the print. In this case, we can just remove this entirely. We have this now. That simplified it a bit. let's get rid of the attachment visibility. And then we'll just move this to a function, generate projectile. We'll move this out. And then we'll call that whenever we want to generate a projectile. What we can do is task.spawn function while true do task.wait for I equals 1 can do task.defer will generate a projectile. This one will come up here. And we'll have our projectiles flying. Like so. And then what we can do to see the number of projectiles is just print a hashtag projectile module.active projectiles. And maybe let's go back up here. Let's do like 1 there. Oh, I just realized that I do that properly. Let me just make sure I've done this. Yeah, that's correctly done. We just need to really jack this up. So let's do like that. Between 8 and 16 studs a second. Oh, yeah, every second. That should be better. There we go. And we're running about 500 projectiles. So that will do any projectile in the game. And if you've got like bow and arrows and all that, you can make it follow the you can do the same thing here where you got the position and last position and you orient the bow. So like your arrow.cframe, cframe.lookat. Your last position. Or in this case, you want your next position. That might be. Well, yeah, you could probably have a look into that. You could probably move this function to like module.final give velocity so you can do this arrow properly, but in this case it'd be like pointing that way. And then you just, yeah, do whatever else you need with that, but yeah, that looks pretty good so far. And then what we can do is some bulk testing. So if we just jack this number up, let's do 100. So you can see we're doing 1500 projectiles. If we actually have a look at the processor here. Let's pause there. So let's see what is taking up the most. So our deferred threads, 60 milliseconds. And then if we have a look at, what's the most expensive one? Do I have on scripts mode right now? No, I don't. Oh, maybe it is that one. Oh, it might be all the beams. It's probably all the beams. If I just disable the beams... Okay, aka literally everything here. And we just run that again. Yeah, there's not much lag there anymore. We can see all of these here. And then if we really want to not do deferring, so if we want to run to like synchronously, we can do that as well. We'll just remove this here. We don't need this updating thing if we're doing it this way. And we'll just have this is updating done. So we try that. We've got all of them running there. And what is this, 42 milliseconds? $42 milliseconds versus 48 milliseconds. So there's a little trade-off there, but that's if you want asynchronous or synchronous, depending on your use case, which most of the time will just be asynchronous anyway. But that's for 100 projectiles, so let's jack this up even further. I'm going to actually move this now to a separate loop. Let me also move that out here. Let's also see if there's anything else I can do to speed it up. So looking around, that's fine. Internal updates. That one. So what we can actually do here is, if we've got a on-hit function, then only we'll do this code then. Otherwise, if we don't have a on-hit function, we'll just continue on and do this. So that means if I go ahead and jump up to here, I'm going to move this to in here now. I'm going to do false, that's a function. Raycast results. That would be projectile hit equals that. There we go. And then we can just disable that if we want, and that should be just way faster as well. Yeah, like all of these are... It's just the defer threads taking forever. If I remove the defer again, it should be a little bit faster. $60 milliseconds. I think that was faster, wasn't it? I'm actually not sure how this works. It was pre... Well, if I did post simulation. $67 milliseconds. Yes, I don't know what's up with it. Might be like, if I do heartbeat, it might be a lot faster. Not even. Or if I just generate projectiles like that, it might be just faster. That looks faster already. 73. You can see all the name calls here. That's one bit of lag. What's the name call? I guess it's got a hidden metatable or something attached to it. But you can see that this loop itself is really quick anyway. I can't see... Oh, it must be the method name call. Or the recast. Is shapecast? Oh, that takes a part. Okay. Spherecast, shapecast. Yeah, so you got a couple options here. I believe actually shapecast is faster than raycast. But you do need to pass in a actual object for that, which we don't have. We're doing points, so... Yeah. And it's also probably Roblox's final events are slow as well. But yeah, that's the projectile system done. You can use this for whatever you want now. That's everything. Not much else here. So we've got our visualizer here. We've got our early termination. We just jump back down to 10 for a moment. So there we go, we got our projectile system. That includes all the basic physics you need, the projectile motion physics from this formula here. Go ahead. So yeah, nice and easy, nothing super complicated, just maybe a little bit to cover. You get a variety of different pieces here put together, like some async updates. This will actually be a lot more expensive once you start doing more in your on projectile hit. So once you start doing reflections, ricochet, all of that in your projectile hit function here, this defer will actually start adding up and it will make a difference. So just for the future, it's probably not doing much right now because the function just returns a number. But yeah, hopefully you found this helpful. Hopefully it was nice that you can explore this. I may do my behavior trees next, although that might be like 4 hours, I don't know. And no promises on when any new videos come out. As you can tell, it's been like 4 months since the last one. So, hope you found this helpful. See you next time.